They called it the workhorse of the Wehrmacht, the German Sd.Kfz.7 heavy tractor, a mechanical beast that had once towed the infamous 88mm flak gun across Europe, hauled howitzers through the mud of Russia, and carried entire artillery crews into battle. To the Allies, it was the very image of German engineering prowess, sleek, powerful, unstoppable. But in the spring of 1945, as the Reich collapsed and the Allies swept across a dying Germany, a handful of American GIs would discover a truth that few strategists in Washington or London had ever considered: that the Third Reich's war machine was built on engines that could not afford to run. For years, Allied soldiers had seen these massive half-tracks littered along the roads of Europe, burned out, abandoned, or disabled. They were symbols of German strength reduced to scrap, but few had actually driven one. That changed in March 1945 when advancing U.S. Army units moving through the Rhineland toward the shattered heart of Germany came across entire depots of intact German vehicles left behind by retreating forces. The temptation was irresistible. These machines looked formidable, even majestic. And so for the first time, American soldiers climbed into the driver's seats of the enemy's machines, turned the keys, and brought to life the deep growl of their Maybach engines. The men expected precision and power. After all, German engineering had become almost a mythic phrase, synonymous with efficiency, innovation, and reliability. Instead, what they discovered changed how Allied military planners thought about warfare itself. Beneath the steel and bravado lay a fatal weakness that no propaganda could conceal. Germany had designed for victory, not endurance. At first, the captured half-tracks impressed everyone. The Maybach engines rumbled with authority, the overlapping road wheels bit into the mud with confidence, and the steering mechanisms seemed robust. They could tow artillery pieces that made the American M3 half-tracks strain and groan. Soldiers wrote home that the German machines felt like driving locomotives, solid, deliberate, almost arrogant. But the admiration faded quickly when they looked at the fuel gauges. Within a few hours, tanks that had been filled to the brim were nearly empty. Drivers who had expected the German half-tracks to match the American M3's 200-mile range were shocked to find themselves running dry after barely 80 or 90 miles. The first assumption was mechanical fault, perhaps leaks, perhaps poorly tuned carburetors. But the tests kept coming back the same. The Sd.Kfz.7 drank gasoline like no machine the Americans had ever seen. When the Ordnance Corps conducted a controlled comparison test, the results were startling. On a standardized 65-mile route, each vehicle towing identical artillery pieces, the M3 consumed 17 gallons of fuel. The Sd.Kfz.7 burned through 63. That's nearly 4 times the consumption for the same job. And in a war where every gallon of gasoline had to cross the Atlantic, survive U-boat-infested waters, and be trucked hundreds of miles to the front, that difference wasn't just mechanical, it was existential. This was not a trivial statistic. According to declassified post-war RAND and U.S. Army Quartermaster Studies, fuel accounted for nearly 45% of the Allied logistical burden in Europe by late 1944. Every convoy, every tanker, every truck carried the lifeblood of mechanized warfare, petroleum. When the Americans discovered that German vehicles like the Sd.Kfz.7 required twice as much fuel for half the range, it revealed a hidden dimension of Germany's defeat. The Reich had built powerful machines, but machines designed for a world where fuel would always be available. The Americans, by contrast, had built their vehicles to live within constraint. From the beginning of the war, U.S. planners understood that gasoline was the choke point of mechanized strategy. It had to be shipped from American wells, refined, transported across oceans, and delivered through a vast pipeline system in Europe. This reality shaped American design philosophy, reliability, and efficiency over raw performance. The The M3 half-track with its 148 horsepower White 160AX engine wasn't elegant, but it was standardized cheap to build and thrifty enough to keep moving when the front lines stretched hundreds of miles ahead. The difference in engineering culture was staggering. The Sd.Kfz.7's Maybach HL62 engine displaced 6.2 liters, a brute force design that favored torque and speed. It was a marvel of power for its time, but its fuel consumption, listed in German manuals at 80 liters per 100 kilometers on roads and up to 160 liters per 100 kilometers off-road, made it catastrophically impractical. American analysts at Aberdeen Proving Ground later calculated that under combat conditions the Sd.Kfz.7 achieved barely 1 mile per gallon. To a soldier in 1945, this meant stopping twice as often for refueling. To a strategist, it meant a war machine that could never sustain a prolonged fight. It's easy to forget that World War II was not just a war of guns and tanks. It was a war of logistics, a contest of who could feed the machinery of war the longest. The Allies understood this. As the U.S. Army's own post-war logistics doctrine stated, strategy without supply is imagination. The Germans, driven by ideology and early victories, built for shock and awe, not sustainability. By 1945, that difference had become visible everywhere. American convoys rolled eastward in steady formation, their engines humming, fuel tanks replenished from mobile depots and field pipelines stretching all the way back to the ports of Cherbourg and Le Havre. The German vehicles, by contrast, sat rusting in ditches empty of gasoline, but still mechanically sound monuments to an empire that had outrun its own capacity to refuel itself. American officers studying captured equipment in the Rhineland began to see the pattern. The fuel inefficiency wasn't limited to the half-tracks. It extended to nearly every category of German military hardware, from the Panther tank, which consumed nearly 2 gallons per mile, to the Luftwaffe's aircraft, which devoured aviation fuel at rates double that of comparable Allied planes. What the Americans were discovering was that Germany had waged war with an economy of excess. It had optimized for battlefield brilliance, not logistical balance. Behind the statistics lay a profound strategic irony. Nazi Germany, so often mythologized for its precision and order, had in fact built a military machine founded on unsustainable assumptions. Synthetic fuel from the Reich's chemical plants, Romanian oil fields under Axis control, and the promise of future conquests were supposed to guarantee endless supply. But by 1944, Allied bombing campaigns and the Soviet advance had strangled every one of those sources. The fuel that once flowed from Ploiești and Leuna was gone, and with it the mobility that had made blitzkrieg possible. American military analysts who examined the Sd.Kfz.7's fuel consumption realized they weren't just studying a vehicle, they were studying the material anatomy of German defeat. Power without efficiency, force without foresight. These were the invisible fractures running through the Nazi war machine. When the tests concluded, the anonymous ordnance captain who had ordered them wrote in his report a single line that would later circulate through the U.S. Army's research departments. A machine that burns twice the fuel delivers half the victory. Those words, understated but prophetic, captured the lesson of 1945 that engineering alone cannot win wars. What matters is the system that sustains the machine, the supply lines, the refineries, the tankers, the fuel trucks, the mechanics, and the planners, who calculate not just how far a vehicle can go, but whether it can return. And in that domain, the unseen realm of logistics, the United States had achieved mastery, while the Reich had engineered itself into exhaustion. By the spring of 1945, the great race across Europe had become a race of gasoline. Behind every tank thrust and infantry advance lay a mathematical truth that even the best generals could not escape. An army's reach was limited by its fuel supply. When the Americans discovered the staggering consumption of the German Sd.Kfz.7, it did more than amuse frontline mechanics. It provided a window into the deeper failure of the Nazi war economy. What the GIs saw on the roads of Germany, powerful machines, stranded tanks, and tractors, sitting silent with empty fuel tanks, was the physical embodiment of strategic exhaustion. From 1939 through 1942, Germany's war machine had surged forward on the promise of conquest. Each new territory brought fresh oil from Austria's shale fields, from Poland, from Romania's Ploiești wells. But after Stalingrad, the equation reversed. The Reich was running on fumes, its industrial base reliant on synthetic fuel plants that could barely meet half the military's needs, even before Allied bombers began systematically targeting them. By mid-1944, U.S. and British air forces had destroyed 90% of Germany's synthetic fuel production capacity. The impact was catastrophic. German fuel output plummeted from 5.7 million tons in 1943 to less than 1 million tons by early 1945, according to declassified post-war data from the U.S. Strategic Bombing Survey. Entire divisions were immobilized. Luftwaffe pilots were grounded for lack of aviation fuel. In the field, half-tracks and tanks were abandoned not because they were damaged, but because they could no longer drink. And yet, despite this reality, German engineers had continued to build vehicles that demanded more fuel, not less. The Sd.Kfz.7 with its 6.4-liter Maybach engine epitomized that contradiction. It was a mechanical masterpiece capable of towing an 8-ton artillery piece through mud, ice, or snow, but it was also a logistical nightmare. At full load, its engine consumed over 160 liters per 100 kilometers, roughly 1.5 miles per gallon. For comparison, the American M3 half-track, less powerful but far more efficient, averaged 3.7 miles per gallon. The difference may sound trivial, but scaled to an army of thousands of vehicles, it became enormous. A U.S. armored division needed about 50,000 gallons of gasoline per day to maintain operations. A comparable German division required 75,000 to 80,000. That 30,000-gallon gap represented more than logistics, it represented survival. As Allied forces advanced deeper into Germany, the lessons became visible in real time. Engineers with the U.S. Ninth Army found hundreds of German vehicles abandoned intact, their fuel tanks dry, their engines still warm. In one after-action report, dated April 1945, an American supply officer noted, "Enemy vehicles found in excellent mechanical condition but lacking all fuel. Crews report complete depletion of stocks. Vehicles now useless except for salvage." Those findings echoed what economists and military analysts would later confirm. Germany's industrial base had been built for short, decisive wars, the kind Hitler had promised in his speeches. The Blitzkrieg campaigns of 1939 to 1941 had been fueled by momentum rapid strikes that seized the enemy's supplies before their own logistics failed. But by 1943, that doctrine had collided with geography and mathematics. The Eastern Front consumed men and fuel at rates the Reich's economy could not replace. When American soldiers at the front discovered that the Sd.Kfz.7's range was barely half that of the M3, they were witnessing not an isolated quirk of design, but the cumulative effect of strategic arrogance. The Germans had optimized their war machine for tactical brilliance at the expense of strategic endurance. American analysts at RAND and the Office of Naval Intelligence would later describe this as a fatal misalignment of engineering priorities. German design bureaus Maybach, MAN, Daimler-Benz had pursued technical perfection as an end in itself, while the U.S. had treated engineering as a function of logistics. American vehicles didn't need to be elegant. They needed to be maintainable, replicable, and compatible with a vast global supply network. This difference extended all the way down to the factory floor. The American M3 half-track was designed to use commercial truck parts, spark plugs, pistons, filters that could be produced by civilian suppliers. Replacement parts were interchangeable across hundreds of thousands of vehicles. In contrast, The Sd.Kfz.7 required specialized German-made components, precision-machined and tightly toleranced. When fuel shortages or bombing disrupted production, even basic maintenance became impossible. The result was a paradox of power. Germany's most advanced vehicles became its most useless. By 1945, this inefficiency had metastasized across every branch of the Wehrmacht. The Luftwaffe's Messerschmitt Bf 109s and Focke-Wulf FW 190s, for instance, were high-performance fighters, but their engines burned aviation fuel at rates that strained even peacetime production. The late-war Me-262 jet, Germany's technological marvel, consumed nearly 3 times the fuel of a piston-engine fighter per flight hour. Meanwhile, the American P-51 Mustang, powered by the Packard-built Merlin engine, could cruise nearly 1,000 miles on internal fuel. It wasn't the fastest or most glamorous aircraft, but it could escort bombers to Berlin and back. That reliability born of design efficiency gave the Allies total air dominance. The same logic applied on land. American engineers calculated that if U.S. vehicles had been as fuel-hungry as German ones, the Red Ball Express, the massive Allied truck network supplying the front lines in 1944, would have needed twice as many tankers and drivers. We would have drowned in our own supply lines, one quartermaster officer later said. Germany did drown in its own logistics. By late 1944, fuel rationing had become so severe that tank crews were instructed to keep engines off during combat preparation, turning them on only seconds before engaging. Pilots were forbidden from taxiing under power and were towed to the runway to save every drop of aviation fuel. Even so, the numbers didn't add up. According to archival data from the Bundesarchiv and the U.S. Air Force Historical Division, the Reich's fuel reserves in January 1945 totaled only enough to sustain full military operations for 2 weeks. 2 weeks against an enemy whose refineries in Texas and California were producing more fuel per day than Germany could refine in a month. So, when GIs climbed into captured Sd.Kfz.7s that spring and marveled at how fast the fuel gauge dropped, they were seeing a microcosm of Germany's strategic collapse. Each refueling stop was a metaphor for a regime that had over-designed itself into extinction. A corporal in the Ninth Army reportedly joked, "The Krauts built Ferraris for a war that needed Fords." His sarcasm wasn't far off. The Sd.Kfz.7 was a magnificent vehicle in isolation, but in a war of attrition, magnificence meant nothing if it couldn't be fed. The U.S. Army learned from that lesson. Within months of victory, analysts at Aberdeen Proving Ground conducted formal fuel efficiency trials on captured German vehicles. Their conclusion was blunt. German tactical engineering was advanced. German logistical engineering was non-existent. In those dry reports, a broader truth emerged, one that reached beyond the battlefield. The failure of Nazi Germany's mechanized warfare wasn't just a military issue. It was an economic one. The same imbalance that had built overpowered fuel-thirsty vehicles had also built a state that could not sustain itself. The Americans didn't win the war because their machines were prettier or faster. They won because their machines fit the system that fed them, and the Germans lost because theirs didn't. By April 1945, as the Allies surged across the Elbe River and the Reich neared its final collapse, the roads of Germany were littered with silent machines. Sd.Kfz.7 half-tracks, Tiger and Panther tanks, Opel Blitz trucks, all abandoned with one simple note scrawled in chalk across their hulls: Kein Benzin, no fuel. What American GIs found in those weeks was more than the debris of war. It was a fossil record of a system that had consumed itself. The German army, once the epitome of mechanized modernity, had ground to a halt not from lack of courage or even weaponry, but from the unglamorous tyranny of arithmetic. Every liter of fuel had to be fought for, and by 1945, arithmetic had won. The captured Sd.Kfz.7s, so admired for their design and craftsmanship, became unintentional teaching tools. When U.S. logistics officers conducted comparative trials, the findings revealed not only technical differences, but philosophical ones. American vehicles, from the humble Jeep to the Sherman tank, were built on the assumption that the battlefield was an extension of the supply line. German vehicles, in contrast, assumed that supply would bend to the needs of the weapon. The Maybach HL62 engine inside the Sd.Kfz.7 was a powerful six-cylinder marvel, but its efficiency lagged far behind. Its compression ratio was deliberately conservative to maintain reliability across variable fuel qualities, yet this decision cost precious miles per gallon. Its fuel injection systems were tuned for performance, not conservation. When run at high torque, as half-tracks often were, it burned through gasoline with gluttonous indifference. American engineers who examined the engines after the war noted something else: the Germans had built complexity into every layer of the vehicle. Overlapping road wheels, double torsion bar suspension, intricate track assemblies, all finely crafted, all difficult to maintain. Each of those design decisions made sense in a workshop. None made sense in a war where the nearest mechanic might be 200 miles away, and the next fuel drum even farther. That philosophy, precision without pragmatism, mirrored the broader trajectory of the Third Reich's industrial strategy. According to the U.S. Strategic Bombing Survey 1946, German engineers consistently prioritized performance metrics like horsepower and armor thickness over mass production and efficiency. The result was a fleet of vehicles that dazzled on paper but faltered in practice. The Panther tank, for instance, boasted an unmatched 75mm gun and sloped armor superior to anything in its class. But it also consumed twice the fuel of an American Sherman and required twice as many man-hours to build. The Sd.Kfz.7, though less famous, followed the same tragic logic. It was powerful, yes. It could tow an 80mm gun through swamps where other vehicles would bog down. But it required fuel convoys, maintenance specialists, and spare parts networks that the crumbling Reich could no longer sustain. By contrast, the American M3 half-track embodied a utilitarian genius that typified Allied design thinking. Its engine was derived from commercial truck models produced by White and Autocar. Its components were standardized. A mechanic who could fix a civilian bus could fix an M3. The vehicle's body panels were simple flat steel, easy to weld, easy to replace. It didn't look as refined as its German counterpart, but it didn't need to. It just worked and kept working. From a macroeconomic view, the story of the Sd.Kfz.7 was the story of Germany's war economy writ small. The Third Reich had entered the war with only 8 million tons of crude oil equivalent reserves compared to America's 100 million plus in 1940. Its answer had been synthetic fuel, a technical marvel, but an economic dead end. Producing fuel from coal required enormous energy input, massive infrastructure, and stable electricity luxuries that Allied bombers methodically erased. According to data from the Rand Corporation and the U.S. Energy Administration's post-war archives, Germany's synthetic fuel plants at Leuna, Bohlen, and Pöhlitz produced around 124,000 barrels per day in 1943. By early 1945, that figure had collapsed to fewer than 12,000 barrels per day. The collapse wasn't just a number. It meant that the entire Eastern Front might receive as little as 1 day's worth of fuel per week. In that environment, a vehicle like the Sd.Kfz.7, consuming nearly twice the fuel of an equivalent Allied vehicle, became an indulgence the Reich could no longer afford. And yet those vehicles kept rolling off German assembly lines until the very end. The bureaucratic inertia of the Nazi war economy refused to adapt, producing machines designed for wars Germany no longer had the means to fight. When captured American mechanics tested the Sd.Kfz.7s in the field, they recorded a range of strange, almost absurd experiences. One after-action report from the 9th U.S. Army described a convoy of mixed vehicles, American M3s, and captured Sd.Kfz.7s hauling artillery pieces through central Germany. After 40 miles, the American half-tracks continued without issue. The German ones were bone dry. Fuel trucks had to detour just to keep them running. The report concluded bluntly, enemy tractors unsuitable for sustained operations due to excessive fuel demand, efficiency poor under all conditions. It was a dry military observation, but in it lay the essence of Germany's defeat. Even in retreat, German armies were handicapped by the same flaw that had defined their wartime philosophy, an obsession with tactical superiority at the cost of strategic endurance. Modern military historians have since recognized the Sd.Kfz.7 as a symbol of this imbalance. A 2021 study by the Swedish Defense Research Agency cited the vehicle as a case study in design optimizing for immediate performance rather than systemic sustainability. The authors compared it to modern, over-engineered weapons platforms that achieve short-term battlefield advantages but demand unsustainable logistics. Their conclusion echoed the lessons American soldiers had learned 8 decades earlier. Power means nothing if you can't fuel it. That realization shaped not just wartime decisions, but post-war doctrine. The U.S. Army's Logistics Manual of 1948, influenced directly by these wartime lessons, included an entire section titled Fuel as a Weapon. It described fuel not merely as a supply item, but as a strategic determinant. Control the fuel, and you control the pace of war. Lose it, and even the best machines become monuments. To the men of 1945, that concept wasn't theoretical. It was visceral. They had driven the captured German half-tracks, heard their engines roar, and watched their fuel gauges plummet. They had seen how the myth of German engineering had collided with the reality of modern logistics. And when they refueled their own M3s and rolled past those silent hulks, they understood what the future of warfare would demand, not the most powerful machine, but the one that could keep moving. The revelation of the Sd.Kfz.7's inefficiency didn't remain confined to the muddy backroads of Germany. It filtered upward through field reports, engineering analyses, and after-action evaluations until it reached the desks of generals and policymakers in Washington and London. What began as a practical frustration for GIs became a lesson in grand strategy logistics. Not firepower decides the lifespan of empires. By April 1945, captured German vehicles were being systematically evaluated at U.S. Army depots in France, Britain, and later at Aberdeen Proving Ground in Maryland. There, American engineers stripped down Maybach engines bolt by bolt, measuring fuel flow compression ratios and torque curves. The numbers were staggering. Under controlled testing, the Sd.Kfz.7's HL62 TUK engine consumed 30–35% more fuel per horsepower than an American White 160AX. When loaded to combat weight, its efficiency fell even further. A technical memorandum from the U.S. Army Ordnance Department, dated September 1945, summarized the issue with cold precision. German heavy tractor, Sd.Kfz.7 represents superior mechanical craftsmanship applied to an unsound logistical concept. Engineering excellence cannot compensate for operational inefficiency. That statement, dry as it was, carried geopolitical weight. It exposed the hidden reason why the Third Reich, despite its tanks, rockets, and jets, could not sustain modern mechanized warfare. Germany had industrial talent, but lacked industrial depth. Its engineers could build masterpieces. Its economy could not feed them. Fuel was only the most visible symptom. The same inefficiency appeared in the production chain itself. German factories required twice as many labor hours to produce a vehicle of equivalent capability compared with U.S. plants. American assembly lines at Ford GM and White Motor turned out trucks and half-tracks with conveyor belt precision using interchangeable parts and standardized fittings. In Germany, production was fragmented among small subcontractors who each built bespoke components, a reflection of a pre-industrial artisan mindset that never fully embraced mass standardization. The result was that while the U.S. could field tens of thousands of M3 half-tracks, Germany struggled to maintain a few thousand Sd.Kfz.7s. By war's end, barely 12,000 had been built in total, most of them lost to fuel starvation rather than combat damage. Economic historians at Cambridge University have since described this as the tyranny of craftsmanship. It produced weapons of superb quality that could not be sustained by an economy at war scale. In essence, the Sd.Kfz.7 was a luxury product fighting an industrial war. Meanwhile, the Americans were redefining what efficiency meant. The U.S. Army Quartermaster Corps had pioneered the pipeline system, a logistical miracle known as Operation Pluto, pipelines under the ocean. Beginning in mid-1944, this network pumped gasoline directly from refineries in southern England under the English Channel to Allied depots in France. By early 1945, Pluto delivered 1 million gallons of fuel per day to the advancing front. The British press hailed it as the artery of victory. Fuel flowed constantly, trucks rolled without pause, and vehicles like the M3 could exploit that abundance because they used it rationally. Even so, Allied planners never took supply for granted. They calculated meticulously how many gallons per mile per tank per day. Efficiency wasn't a moral virtue, it was a survival skill. In contrast, Nazi Germany's strategic fuel plan had collapsed under its own assumptions. The synthetic fuel plants at Leuna and Pulitz, targeted by the U.S. 8th Air Force during Operation Point Blank, were reduced to rubble. A declassified RAND analysis later showed that after May 1944, German aviation fuel output fell by 89% in just 6 months. Without fuel, not even the most advanced weapon could move or fly. Frontline soldiers saw the effects immediately. American patrols frequently found intact Luftwaffe aircraft parked along runways, their wings pristine, their tanks empty. Panzer crews drained fuel from trucks and motorcycles to fill their tanks for one final engagement. One report from the 3rd Armored Division noted that German tanks were being towed into battle by horses, a surreal regression to 1914 in a supposedly mechanized army. When American crews experimented with captured Sd.Kfz.7s, they understood instinctively what those empty tanks meant. Every time their German half-track sputtered to a halt after 80 miles, it illustrated the fatal equation that had undone the Reich: tactical brilliance minus logistical capacity equals defeat. The British historian Sir Basil Liddell Hart later captured this idea succinctly in his 1948 book, The German General's Talk. Germany's weapons were often finer than ours, but they were too fine. They were built for victory in theory, not for survival in practice. The Sd.Kfz.7 was a perfect metaphor for that observation, a vehicle too perfect to endure imperfection. As post-war analysts assembled their data, a new doctrine began to form. The U.S. Army Field Manual 105, 1949, written under General Omar Bradley's supervision, explicitly cited fuel economy as a planning parameter for all future mechanized units. It treated gallons as ammunition. In military academies, the lessons of 1945 entered the curriculum. Mobility is limited by logistics. Logistics is limited by fuel. Even economists outside the military took note. A 1952 study by the World Bank on wartime industrial conversion concluded that the Allied victory had proven the economic superiority of standardized efficiency over bespoke engineering. The Sd.Kfz.7, once admired as a masterpiece of design, became a cautionary tale in engineering schools, a warning that beauty without practicality is failure by design. In retrospect, That half-track's roaring Maybach engine symbolized Germany's delusion of endless momentum, a belief that willpower could substitute for infrastructure. The Americans, pragmatic to the core, never believed that. They built systems, not symbols. The difference decided the outcome of the most industrialized war in history. And so as May 1945 dawned, and Berlin burned those abandoned German vehicles, told the story of a nation that had engineered itself into immobility. The Sd.Kfz.7 had once pulled the mighty 88mm gun, the terror of Allied tanks and aircraft alike, but in the end, it could not even pull itself. When the war ended, the Sd.Kfz.7 was more than a piece of captured hardware. It was a revelation about how empires collapse not from explosions, but from exhaustion. The American soldiers who had driven those hulking German half-tracks understood it instinctively. What they learned on the back roads of the Rhineland would later be confirmed by economists, generals, and historians. Logistics is destiny. At the heart of that destiny was fuel and the American mastery of it. During the final months of the war, the Allied logistical network was a moving city of pipes, drums, and convoys stretching from the ports of Antwerp and Cherbourg to the front lines in Germany. Over 1 million gallons of gasoline flowed to American forces each day. It was an achievement of coordination as much as production one that no other belligerent in history had matched. The Germans, by contrast, were living through the opposite experience, a complete logistical implosion. In February 1945, internal Wehrmacht reports estimated that 60% of all German armored vehicles were immobilized at any given moment for lack of fuel. Even elite divisions such as the Panzer Lehr could only operate at half strength. The Luftwaffe, once Europe's most formidable air force, had been reduced to training glider pilots because aviation fuel reserves were gone. In that context, the Sd.Kfz.7 became a case study in what RAND analysts decades later would call negative force multipliers technologies, so demanding that they consume more resources than they deliver in combat advantage. A machine that required a convoy of fuel trucks just to operate had ceased to be an asset. It was a liability. At the Aberdeen Proving Ground in Maryland, American ordnance engineers formalized what field soldiers already knew. Their post-war report, Evaluation of German Tracked Tractors, Vulner 3 Sd.Kfz.7, concluded that the Maybach engine was an example of elegant over-engineering in an economy that could not afford elegance. It was mechanically flawless under laboratory conditions, but completely unsuited to prolonged field operations. When they compared it with the M3 half-track's white 160AX engine, the difference was stark. The American motor produced slightly more horsepower per liter, yet required 30% less fuel to do so. Its compression ratios, lubrication systems, and carburation were optimized for mass production tolerances, not perfection. Where the Maybach engine demanded precision maintenance and high-octane fuel, the white could run on whatever was available. That single contrast explained the broader divide between the two nations. The Germans designed for peak performance, the Americans designed for persistence. The post-war economic data reinforced that conclusion. Germany's total fuel production in 1944, both natural and synthetic, equaled roughly 57 million barrels, while U.S. domestic production that same year exceeded 1.3 billion barrels, according to the Department of the Interior's petroleum statistics. The disparity was astronomical. Even if German fuel plants had operated at full capacity and remained untouched by Allied bombers, they could never have matched the consumption demands of their own vehicles. The paradox of German engineering, as one analyst at the U.S. Strategic Bombing Survey put it, was that the more advanced their machines became, the less usable they were. The Tiger and Panther tanks that symbolized German military might suffered from exactly the same disease as the Sd.Kfz.7: excessive power, insatiable fuel needs, and catastrophic inefficiency. American tank crews who tested captured Panthers after the war calculated that the vehicle achieved barely 0.5 miles per gallon, half the range of a Sherman. German recovery vehicles and heavy tractors performed similarly. One American major summed it up with dry humor: "If you gave them enough fuel, they'd beat us." But that's the point, they never had enough fuel. What these soldiers sensed intuitively would later form the basis of a new kind of military economics. The U.S. Army and RAND began incorporating fuel cost per combat mile into their early Cold War modeling. The lesson from the Sd.Kfz.7 was mathematical, as much as moral mobility wasn't a given. It was a budget. This understanding reshaped post-war military design. The M59 armored personnel carrier, introduced in 1954, was engineered to achieve at least 4 miles per gallon, a small number by civilian standards, but a remarkable improvement in battlefield logistics. Later, the aluminum-bodied M113 would nearly double that efficiency. In both cases, engineers cited the lessons of the German half-tracks as a guiding principle in their reports. At the same time, U.S. strategic planners began to treat oil as an instrument of statecraft. The wartime realization that industrial victory required energy abundance led to the establishment of vast peacetime reserves and partnerships with oil-producing nations. As historian Daniel Yergin wrote in the prize The Epic Quest for Oil, Money, and Power, World War II taught America that oil was not just the fuel of engines, but the lifeblood of global power. Germany had learned that lesson too late and in reverse. By 1945, the Reich was scavenging every drop it could find, even siphoning aviation fuel from grounded aircraft to keep trucks moving. Field diaries from German officers capture a haunting monotony. Every page begins with requests for fuel that never came. For those on the ground, the consequences were immediate. One American report described how a captured Sd.Kfz.7, used by a U.S. artillery unit to tow a 155mm howitzer, ran dry midway through a mission despite being fully fueled that morning. The crew had to abandon the German tractor and finish the job with an M3. "We gave up on it," the report read. "Too much power, too little purpose." That line became a metaphor for an entire war machine. Post-war historians from the London School of Economics later calculated that if all German vehicles had matched American fuel efficiency, the Wehrmacht could have extended its operational range by roughly 35%, potentially altering early war campaigns in North Africa and Russia. Yet the same report added that such efficiency was impossible under Nazi economic ideology, which glorified technical perfection over practical sufficiency. The Sd.Kfz.7 thus stands as both a symbol and a warning. It showed how a nation that prized engineering brilliance could still lose to one that prized logistical discipline. It also demonstrated something more profound, that the future of warfare belonged not to the boldest design, but to the system that could sustain it indefinitely. In 1945, that system belonged to the Americans, as GIs refueled their own half-tracks and rolled past the silent columns of abandoned German machines. They could not have known that the lessons they learned would shape the next century of military thinking, from Korea to Kuwait. Yet in their casual observations in those fuel consumption notes, scribbled into field reports, they had uncovered the fundamental truth of modern war victory is the art of movement, and movement begins at the pump. The irony of the Sd.Kfz.7 story is that it was in every mechanical sense a triumph of craftsmanship. To a mechanic's eye, it was magnificent, precision-machined gears, elegantly cast cylinders, armored panels, fitted so seamlessly that seams looked sculpted. German engineers had achieved something close to perfection in metal, yet that perfection existed in a vacuum. It was designed for a war Germany could not sustain, for a fuel supply that no longer existed, for an empire already bleeding out through its industrial arteries. By the time American engineers got their hands on captured examples in mid-1945, the half-track's mystique was fading. The first report from Aberdeen Proving Ground described the Sd.Kfz.7 as an engine without an economy. The analysis was blunt. While it could tow the famed 88mm flak gun, with ease its appetite for gasoline was insatiable. When the Aberdeen team graphed fuel consumption against power output, the German vehicle's curve resembled a rocket trajectory, impressive but unsustainable. The deeper they looked, the clearer the pattern became. The Maybach engine's low compression ratio, roughly 6.41, had been chosen to handle variable quality fuels available in wartime Europe. This was sensible at first, but it meant poor thermal efficiency. The carburetors ran rich to avoid stalling under load-wasting fuel with every stroke. Even the final drive gearing favored brute pulling power over efficiency. Every decision favors power over endurance, the report concluded. American vehicles embodied the opposite logic. The M3's white 160AX engine used a 6.5-liter displacement, but with tighter combustion tolerances and simplified intake geometry. Its carburation was adjustable in the field. Its parts were designed for interchangeability. A broken pump could be replaced with one from a civilian truck. To American engineers, the comparison was almost philosophical. The M3 was democratic engineering. The Sd.Kfz.7, aristocratic engineering. One valued practicality, the other prestige. That divide echoed beyond the battlefield. When post-war economists analyzed how industrial cultures influence warfare, the Sd.Kfz.7 became a recurring example. In 1947, a RAND analyst named Herbert Goldhamer wrote a report titled The Economic Psychology of Armies. He argued that Germany's defeat was not just military, but cultural, a triumph of system over virtuosity. The Americans, he wrote, built mediocrity that endured. The Germans built excellence that collapsed. Every captured Sd.Kfz.7 sitting rusting in a German field in 1945 illustrated that verdict. From a logistical standpoint, the German design philosophy created cascading inefficiencies. Each Sd.Kfz.7 required twice the refueling trips, which meant twice the number of fuel trucks and drivers. Those trucks burned fuel themselves, compounding the problem. In a modern analysis, RAND researchers call this the logistics multiplier effect. Every inefficient machine adds invisible layers of consumption to the system that sustains it. In late-war Germany, those layers had become crushing. Historical data from the U.S. Strategic Bombing Survey confirms that by March 1945, less than 20% of German armored vehicles were operational at any given time, most sidelined for lack of fuel rather than mechanical failure. This was the final absurdity. The Wehrmacht, once the most mechanized army on Earth, had become an army of immobile machines. Even the great battleship Bismarck had been lost to similar blindness, a vessel of enormous power built without a sustainable supply chain to support it. By 1945, that same blind faith in technical supremacy had infected every level of German design, from jet aircraft to half-tracks. The American soldiers who drove captured Sd.Kfz.7s sensed all of this in miniature. They didn't need charts or post-war studies. They felt it every time they filled the tank and watched the gauge drop. A sergeant with the 9th Army reportedly joked, "You could almost see the gas evaporate through the hood." His humor masked a deeper truth: they were witnessing an empire literally running out of energy. For the United States, that realization became doctrine. In the late 1940s, when Pentagon planners drafted the first modern logistics manuals, they treated fuel efficiency as a measure of national strength. A 1949 field directive from General Omar Bradley's office included a new term: mobility index, the ratio of a unit's effective combat range to its total fuel consumption. That metric, directly inspired by wartime comparisons between German and American vehicles, shaped decades of procurement policy. It also changed how America approached industrial warfare. The government's wartime partnership with oil companies, Standard Oil Texaco Gulf, evolved into the post-war Strategic Petroleum Reserve and Global Energy Strategy. The logic was simple. Whoever controlled reliable energy supply controlled the next war before it began. In hindsight, the Sd.Kfz.7 represented a paradox that extended far beyond its 57-gallon tank. It embodied the illusion of invincibility that had guided Nazi Germany, a belief that power could replace planning, that perfection could defy limits. But in the harsh mathematics of total war limits, always win. One American colonel, who oversaw captured equipment evaluations, summarized the lesson more poetically than any economist could. The Germans built machines that asked too much of the world, he wrote. We built machines that asked only what the world could give. When the engines finally fell silent in 1945, that distinction had decided more than the fate of a vehicle. It had decided the fate of a civilization built on the wrong kind of strength. In the months following Germany's surrender, the Sd.Kfz.7 continued to serve not in battle, but as evidence. At Allied proving grounds, it was studied, measured, and dissected, like a fossil of an extinct predator. Engineers, economists, and even sociologists found in its steel anatomy the story of a society that had confused technical brilliance for strategic wisdom. At Aberdeen proving ground, technicians ran one captured half-track after another through controlled endurance trials. They timed acceleration, recorded torque output, and charted fuel use over terrain. The verdict was consistent. Under ideal road conditions, the Maybach HL62 engine consumed around 80 liters per 100 kilometers. On mixed terrain, 160 liters. Even the best-maintained specimen achieved barely 1.5 miles per gallon. The reports read like autopsies of overambition. Exceptional traction, unacceptable efficiency, one engineer scrawled in the margin. Across the Atlantic, British analysts at the Mechanical Warfare Experimental Establishment conducted their own evaluations. They admired the Sd.Kfz.7 suspension. Its interleaved road wheels gave unmatched stability, but they called its maintenance demands absurd for a vehicle in wartime service. One clogged bearing could immobilize an entire tractor. In a nation already starved of fuel time and manpower, that was ruinous. By late 1945, American economists had begun drawing parallels between the German approach to vehicle design and the broader failures of the Nazi economy. The U.S. Strategic Bombing Survey's Economic Division concluded that German industrial policy favored excellence at the expense of endurance. It produced what one analyst dubbed a nation of prototypes, magnificent machines that existed in too few numbers and consumed too many resources to make a strategic difference. That diagnosis echoed far beyond military circles. At the Bretton Woods Conference earlier that year, where the post-war global economic order was being drafted, American delegates spoke privately of the war as a contest between industrial philosophies. The German model, centralized and perfectionist, had collapsed under its own weight. The American model, decentralized and standardized, had outproduced, outsupplied, and ultimately outmaneuvered its rival. The Sd.Kfz.7 sitting on a test track in Maryland was the mechanical proof of that outcome. Even captured German officers recognized the irony. General Heinz Guderian, interviewed during the Nuremberg interrogations, lamented that our engineers built masterpieces, but they forgot the soldier. He recalled watching entire panzer regiments stranded for lack of gasoline. The machines were ready, the men were willing, but the fuel was a ghost. The contrast with the Americans was impossible to ignore. U.S. forces had turned fuel into a weapon as decisive as any bomb or bullet. Through operations like Pluto and the Red Ball Express, they delivered energy across continents with industrial rhythm. The Sd.Kfz.7, meanwhile, stood as a monument to a different rhythm, one that burned bright and fast until it consumed itself. By 1946, the captured half-tracks were being shipped to training ranges or scrapyards. A few were retained for museum collections. Others found short second lives in European armies that lacked better equipment. Czechoslovakia's post-war army, for instance, operated a small fleet until the early 1950s. But even there, fuel complaints persisted. Superb traction, disastrous economy, read a Czech maintenance log from 1949. The lesson, however, endured far longer than the machines. In the United States, the Army Logistics College began teaching case studies on fuel economy using wartime data. The Sd.Kfz.7 appeared beside the Panther tank and the Messerschmitt Me 262 jet as examples of operational overreach. The accompanying directive was clear: no design, however advanced, is successful if it cannot be sustained in the field. This insight seeped into doctrine across the early Cold War. When the Pentagon launched the M-series vehicle program, efficiency was written into every specification. Engineers were ordered to calculate not just horsepower or armor thickness, but gallons per combat mile. It was a bureaucratic term born from a battlefield truth first noticed by tired GIs in the spring of 1945, watching German fuel gauges sink. Strategists soon extended that logic to geopolitics. The post-war U.S. obsession with global oil access from the Middle East to the Gulf of Mexico was a direct consequence of these wartime realizations. In 1946, the State Department's Petroleum Division issued a confidential memorandum. Energy is not only the foundation of domestic prosperity, but the instrument of sustained military mobility. The German case demonstrates the strategic collapse that follows from dependence without surplus. What had begun as a mechanical curiosity, a thirsty German tractor, had evolved into a philosophy of global power. By the time the last Sd.Kfz.7s disappeared from service, replaced by more efficient post-war vehicles, the lessons they embodied had already reshaped the industrial world. Every tank, every jet, every carrier group designed in the decades to come would be haunted by the question the Americans first asked on the roads of the Rhineland: how far can it go before it runs dry? For Germany, that question had come too late. By 1947, the post-war reconstruction of Europe was underway, but the lessons from the Sd.Kfz.7 were already influencing how nations thought about rebuilding not just machines, but systems. The American military's meticulous post-war studies from Aberdeen to the Pentagon's Research and Development Board concluded that fuel efficiency was not merely a technical feature, it was a metric of national resilience. The Sd.Kfz.7 embodied the opposite of that resilience. In its gleaming steel and roaring Maybach engine, American analysts saw the perfect metaphor for the Third Reich's collapse, a regime that equated sophistication with superiority, blind to the fact that modern warfare rewarded endurance over elegance. One RAND memorandum from 1948 phrased it bluntly: Germany built performance machines in a world that demanded performance systems. To keep an army moving, the Americans realized every drop of gasoline had to travel through a pipeline of infrastructure labor and supply chain predictability. Germany had severed its own pipeline long before the Allies bombed its refineries. Synthetic fuel plants at Leuna, Böhlen, and Pölitz could produce vast quantities of high-octane gasoline, but only if coal and hydrogen shipments arrived on time. When rail lines were cut, the entire system collapsed, like a lung starved of oxygen. In contrast, the U.S. petroleum network functioned like a living organism. Tankers from Texas refineries steamed across the Atlantic, feeding depots in Britain and North Africa. Convoys of trucks rolled through France along meticulously planned supply corridors. This logistical choreography allowed a Sherman division to burn through 60,000 gallons a day without fear of immobilization. That same level of consumption would have paralyzed a German panzer division. The Sd.Kfz.7's downfall, therefore, was not mechanical, it was metabolic. Its body was powerful, but its metabolism could not sustain itself. Its 6.4-liter Maybach engine drank faster than its nation could breathe. In 1945, the average German soldier consumed 3 times more fuel per kilometer than his American counterpart, and that imbalance extended from the smallest motorcycle to the largest Tiger tank. Germany had built an army optimized for blitzkrieg, not for a marathon. The American GIs who had driven those captured half-tracks would never have described it in such academic terms, but they understood the reality viscerally. One soldier from the 3rd Armored Division wrote home, "These Kraut rigs run strong, but you watch the gauge fall like a clock. You'd think it leaks, but it's just thirsty." His words, preserved in an Army historical archive, capture the moment when raw observation became strategic insight. At Aberdeen, engineers continued their tests throughout 1946. They tore down the Maybach HL62 engines, noting the extraordinary machining tolerances and high-grade alloys used in its pistons and valves. Then they did the same to an American White 160AX engine. The difference, as one engineer put it, was the difference between a violin and a banjo. The violin produced beauty. The banjo endured every bar fight. America's advantage was that its weapons could be built by the millions repaired by farm hands and kept running with spare parts from any commercial depot. This philosophy soon became the backbone of U.S. military-industrial policy. Standardization, the principle that any bolt or bearing from Detroit would fit any field vehicle in France, proved as decisive as any battlefield victory. The Sd.Kfz.7, with its bespoke components and precision assemblies, could never have been mass-produced on that scale. Each one demanded craftsmanship in a war that demanded quantity. Economists in the Marshall Plan administration took note. As they rebuilt Europe's industries, they favored modular, standardized production systems modeled on American wartime logistics. The idea was not only to prevent economic collapse, but to ensure that no European power would again make the same mistake Germany had made, betting its survival on machines too advanced to maintain. Yet for all its inefficiency, the Sd.Kfz.7 retained a strange allure. Museum curators and military collectors prized it as a relic of lost precision. Photographs of the vehicle towing its 88mm flak gun across North Africa or the Russian steppe still circulated in post-war magazines. It looked indestructible, unstoppable. But those who had studied it knew that its strength was an illusion bought with unsustainable cost. Every mile of progress had been paid for in gasoline that Germany could no longer afford. One U.S. Army historian later described the Sd.Kfz.7 as a machine that won its first 100 miles and lost every mile after. That observation became the opening line of a 1952 lecture at the Command and General Staff College at Fort Leavenworth, titled Logistics and the Decline of the German Army. It wasn't just about a vehicle. It was about the principle that the future belonged to the side that could move cheaply, not just powerfully. The broader geopolitical lesson was unmistakable. By mastering logistics and energy distribution, the United States had forged a template for global dominance that would persist throughout the Cold War. Oil pipelines replaced supply convoys, tankers replaced troop columns, and fuel efficiency became a measure of strategic independence. The Sd.Kfz.7, though long melted down or rusting in museums, had left its ghost in Pentagon white papers and RAND simulations of future wars. Even decades later, when analysts discussed the Vietnam or Gulf Wars, they invoked the same principle: every gallon of fuel carried to the front costs 4 gallons in the journey. The American solution was to make every machine from trucks to tanks worth that cost. The German mistake had been to design machines that magnified it. If the Tiger tank symbolized Germany's martial pride, the Sd.Kfz.7 symbolized its logistical arrogance, a refusal to believe that quantity and simplicity could defeat craftsmanship and power. In the end, it was not a lack of courage or talent that doomed the Wehrmacht, but the quiet arithmetic of efficiency. And that arithmetic, once learned, would govern the world long after the last engine fell silent. By 1948, the Sd.Kfz.7 was no longer just a piece of war debris, it had become a parable for an entire era of military thought. American strategists, economists, and engineers all seemed to return to it when defining what sustainability meant in warfare. They had discovered almost by accident that a nation's fuel lines were as decisive as its front lines. The Maybach engine that once pulled 88mm guns across Europe now sat under bright fluorescent lights in a disassembly hall at Aberdeen. Engineers measured every piston, every valve, every camshaft. The verdict was unanimous. The German half-track was a masterpiece and a disaster. It was precise where it should have been, flexible complex where it should have been simple. One analyst compared it to a Swiss watch built for a coal mine. In the same report, the engineers noted something quietly revolutionary. The white 160AX engine of the American M3 half-track could be serviced by any Army mechanic with commercial truck experience. A field depot could strip and rebuild one in less than 6 hours using common tools. By contrast, the Sd.Kfz.7's Maybach required precision timing gauges, specialized carburetor wrenches, and trained technicians. The difference was not merely technical, it was social. The American vehicle assumed an army of citizens. The German vehicle assumed an army of specialists. That distinction would ripple far beyond the workshop floor. As the U.S. built its post-war global strategy, it relied on systems designed for replacement, not perfection. The very same philosophy that allowed GIs to fix half-tracks in muddy fields would soon define the Marshall Plan, the NATO logistics network, and even the infrastructure of the Cold War itself. Mobility and standardization became the DNA of American power. Germany's wartime philosophy, by contrast, had treated every machine as a handcrafted ideal. In the words of historian Adam Tooze, the Reich built an economy that worshipped precision at the expense of replication. The Sd.Kfz.7 was proof, every nut and bolt, a triumph of craftsmanship, every mile an act of waste. When Rand's logistics division published its first post-war study in 1949, it drew directly on data from captured German vehicles. The study, titled Energy Expenditure and Force Mobility in Modern War, introduced a term that would dominate Cold War planning: Energy Density Index (EDI), the ratio of combat output to fuel consumption per ton. The M3 scored 1.4. The Sd.Kfz.7 barely reached 0.7. Rand analysts noted dryly, had the German army's EDI approached even 1, the duration of the war in Europe might have extended by 1 year. That realization reshaped not only military design, but the geopolitics of oil. U.S. planners now saw petroleum not simply as a commodity, but as a vector of dominance. From the Persian Gulf to Venezuela, American policy in the late 1940s and 1950s revolved around ensuring that the fuel which had won the last war would never again run short in the next. The Sd.Kfz.7, though long scrapped, had become part of the intellectual foundation for the U.S. global energy architecture. For Germany, the machine lingered as a ghost of lost grandeur. Post-war German engineers, many working for Allied manufacturers, quietly acknowledged that the half-track had been over-designed. In a 1950 article for Autotechnische Zeitschrift, a former Maybach engineer wrote, "We built for the war we wished to fight, not the one we had." He described how the pressure to demonstrate technological superiority had overridden calls for practicality. We could build anything, he admitted, except a future. Meanwhile, at Fort Leavenworth and the U.S. Army Command and General Staff College, instructors used the Sd.Kfz.7 as a cautionary case. The lesson was stark. A weapon that can't be fueled is not a weapon, it's terrain. Students were told to imagine an entire Panzer Corps immobilized because its logistical chain had collapsed. That exercise was no abstraction. It had happened across the Rhine and the Ardennes, where rows of abandoned half-tracks testified to the end of a mechanized dream. In that sense, the American fascination with the Sd.Kfz.7 became almost moral. It affirmed a belief that democracy's strength lay not in perfection, but in persistence. The M3's simplicity, the interchangeable bolts, the field-forged repairs, all were metaphors for a society built on adaptability rather than obsession. Decades later, when NATO standardized fuel grades and vehicle parts among its member states, staff officers traced the idea back to wartime lessons. The bureaucratic term interoperability had its origin in the chaos of 1945, when American units discovered that they could not even refuel a captured German truck without custom fittings. From that moment forward, no alliance could afford such incompatibility. By the early 1950s, only a handful of Sd.Kfz.7s remained operational in Europe. The rest were melted down for steel, their Maybach engines dismantled for study or spare parts. Yet their influence persisted. In the Pentagon's archives, the phrase German fuel paradox appeared in briefing papers about everything from tank design to early jet aircraft. Each time the message was the same: never confuse capability with sustainability. When the Korean War erupted in 1950, American supply officers invoked the same logic that had defeated the Reich. They built fuel dumps, pipeline battalions, and convoys before the first shot was fired. The result: the U.S. maintained mobility across a peninsula where other armies bogged down. Behind that operational success lay a forgotten half-track and a handful of field reports from 1945, scribbled by men who had simply wanted to see how far a German engine could go on a tank of gas. The answer, barely 90 miles, became a line of data that changed the shape of military history. By the early 1950s, the Sd.Kfz.7 had faded from roads and depots, but its shadow loomed over every staff college classroom and engineering laboratory that studied the Second World War. To the untrained eye, it was just another relic, an obsolete half-track rusting beside old Shermans and Cromwells in military museums. But to the men who had driven it, and to the planners who had studied it, the German machine represented the most expensive kind of brilliance, the kind that could not sustain itself. At the Aberdeen Proving Ground Museum, an officer once explained to visiting cadets why the German half-track was displayed beside the American M3. These two fought the same war, he said, tapping the Sd.Kfz.7's thick fender, but only one of them could finish it. That single remark summed up an entire generation's understanding of mechanized warfare. In the American imagination, the Sd.Kfz.7 became shorthand for an empire that had overreached its power, too concentrated its logistics, too brittle. The U.S. Army's new design philosophy, codified in its Technical Bulletin 5545 of 1952, enshrined the lessons learned from that captured machine. Every vehicle would be rated not only for horsepower and armor, but for sustainment efficiency, the ratio of battlefield endurance to logistical cost. From the M48 Patton tank to the M35 Deuce and a half-truck, the ethos was clear: simplicity wins wars. Across the Atlantic, NATO's newly formed logistics councils used the same logic to bind their fledgling alliance together. Standardized parts, shared fuel grades, and interchangeable fittings were no longer just conveniences, they were geopolitical commitments. The Red Army's numerical superiority could only be offset by Western efficiency. Every bolt, every gasket, every gallon had to count. It is difficult now, in an age of digital warfare, to appreciate how revolutionary that idea was in the late 1940s. Before the war, no army had measured its strength in gallons or miles per ton. Yet the defeat of Nazi Germany turned those abstractions into doctrine. RAND, the Office of Naval Research, and the fledgling CIA all funded studies on what they called logistics vulnerability indices. The conclusion was sobering: the mightiest army in the world could be undone by an empty fuel drum. Even as the Cold War began, the Sd.Kfz.7's legacy lingered like a warning. American officers studying Soviet equipment after Korea noted that while Soviet tanks were rugged and fuel-hungry, Moscow's oil reserves and centralized supply networks allowed it to sustain inefficiency. The West, by contrast, compensated through precision logistics, a direct heir to the wartime lesson of the half-track. Efficiency became its own form of deterrence. At the same time, historians began to reinterpret the German defeat not as a failure of courage or strategy, but as a triumph of arithmetic. The U.S. strategic bombing. Survey's final report on oil campaigns 1946 stated it plainly. The destruction of Germany's fuel system, compounded by the inefficiency of its engines, ensured paralysis regardless of battlefield success. In that sentence lay the essence of the Sd.Kfz.7's tragedy. It was a vehicle designed for a war Germany could not afford to fight. Every time its Maybach engine roared, it consumed a resource the Reich could no longer replace. In its chrome and grease, the half-track embodied the same arrogance that had driven German policy from Warsaw to Stalingrad, the belief that speed and strength could overcome scarcity. For American soldiers who had driven it in 1945, that arrogance had been both awe-inspiring and absurd. In memoirs and interviews recorded decades later, many recalled the experience vividly. It felt like a tank with a steering wheel, one GI said. Power for days, but you couldn't take it anywhere. You'd run dry before lunch. Another described how they would siphon gasoline from jeeps just to get the German half-track back to camp. It looked like victory, he said, but it ran like defeat. That sentiment echoed through post-war military culture. The U.S. Army's Field Manual 101-10, issued in 1954, carried an entire section titled Lessons in Resource Allocation from the European Theater. Among its case studies, the Sd.Kfz.7's fuel consumption compared to the M3. It concluded with a stark line: power without endurance is failure in motion. This philosophy eventually filtered into civilian life as well. The post-war American automotive boom drew on the same engineering lessons that had defined wartime production. Detroit's factories, which had once churned out half-tracks and tanks, now produced millions of cars using standardized interchangeable components, a concept perfected in the crucible of logistics. Even commercial fuel economy standards decades later could trace their lineage back to wartime calculations about how far a convoy could move on a gallon. Meanwhile, in divided Germany, engineers rebuilding the nation's automotive industry studied their own wartime designs with a mix of pride and regret. Companies like Daimler-Benz and Maybach pivoted toward efficiency. We learned the hard way, one former designer said in 1955. Precision without pragmatism is a luxury a nation can't afford. The Sd.Kfz.7 had taught them that lesson too late to save the Reich, but just in time to shape West Germany's economic rebirth. And yet, the machine's symbolic power endured. In documentaries and newsreels, footage of the Sd.Kfz.7 towing the 88mm flak gun remained one of the enduring images of Nazi Germany's war machine. To viewers, it represented German might. To scholars, it represented German blindness. Its broad tracks and elegant engineering looked unstoppable, but in the archives lay the truth. Its range was shorter than the battlefield it was meant to dominate. The final irony was that the Americans, not the Germans, carried the spirit of the Sd.Kfz.7 forward by learning from its failure. They built vehicles that could cross continents on a single logistical chain. They created alliances sustained not by ideology, but by supply. They understood that empires are measured not in power projected, but in power maintained. The Sd.Kfz.7 had shown them what happens when that balance collapses. By the mid-1950s, the Sd.Kfz.7 had become a ghost in military thought, invoked not for its might, but for the caution it embodied. Every generation of officers who passed through Fort Leavenworth or Sandhurst learned its name not as a hero's machine, but as a case study in failure by excess. In war colleges and RAND seminars, the phrase, the Sd.Kfz.7 principle, began to circulate shorthand for any system that dazzled in performance, yet bankrupted itself in operation. Behind that principle lay a profound shift in strategic thinking. The Second World War had forced militaries to confront an uncomfortable truth: efficiency, not grandeur, wins industrial wars. When RAND systems analysts began modeling logistics for atomic-age conflict, they cited the German half-track alongside the V-2 rocket as examples of unsustainable innovation. The V-2 could terrify London, but at a cost that consumed Germany's last reserves of alcohol fuel. The Kfz.7 could tow an 88mm gun across Europe once. Both were triumphs of ingenuity that ignored the arithmetic of resources. The Americans, by contrast, had turned logistics into a science. The Pentagon's new Office of Logistics Research published its first report in 1955, Mobility and National Power. The opening line read, "Wars are no longer won by generals, but by quartermasters." Embedded in that doctrine was the lesson written in gasoline on the roads of the Rhineland. The United States had discovered that the ability to sustain motion, to move, refuel, repair, and repeat, was the purest form of strength. Across the Atlantic, West German engineers rebuilding their industries took the same lesson to heart. The economic miracle of the 1950s, the Wirtschaftswunder, was built not on heavy, wasteful machinery, but on compact cars and efficient engines. The same nation that once built the thirsty Maybach HL62 now produced the Volkswagen Beetle, a symbol of economy and simplicity. "We learned our lesson in the mud of Russia," one engineer told Der Spiegel in 1953. "Our machines were too good to live." In those few words, he captured a nation's reckoning with its own technological arrogance. Meanwhile, American doctrine institutionalized the opposite creed: redundancy over perfection, adaptability over precision. The U.S. Army's Field Manual 1015 defined logistics as the art of sustaining imperfection. In lectures, officers invoked the Sd.Kfz.7 as a warning against designing a machine that consumes itself faster than the enemy can destroy it. The lesson resonated far beyond military design into the planning of entire alliances' economies and even foreign policy. When NATO debated standardizing its fuel and ammunition calibers in 1956, a British delegate reportedly held up a photo of the Sd.Kfz.7 and said, "This is why we standardize." The room fell silent. The message was understood. The image of that stranded German half-track empty tanks glinting under a gray sky had become a symbol of disunity's cost. In America, the legacy extended even into popular culture. Hollywood war films of the 1950s often depicted German machines as monstrous, overbuilt, doomed reflections of a philosophy that worshipped form over function. The American Jeep, small and unassuming, became the cinematic emblem of victory: modest, reliable, unstoppable. It was the M3's spiritual descendant and the antithesis of the Sd.Kfz.7. Yet behind every retelling lay the same quiet truth that the soldiers of 1945 had learned firsthand: power is meaningless without reach. A machine's strength is measured not by how loud it roars, but by how far it can go before silence. When historians from the U.S. Army Center of Military History compiled their definitive report, German Logistics, 1939 to 1945 and 1957, the Sd.Kfz.7 occupied an entire chapter. The conclusion was elegant in its simplicity. The Wehrmacht's failure was not in courage, nor even in design, but in comprehension. It mistook performance for endurance. By then, the half-track itself was nearly extinct. A few survived in Czechoslovakia, and France used for forestry or as recovery vehicles. Others, stripped of their engines, served as monuments in war cemeteries. One still stands today in Koblenz, its hull rusted to a dull brown, its wheels half buried in soil. Tourists photograph it for its imposing frame. Few realize they're looking at the ghost of a system that consumed its own future. In a sense, the Sd.Kfz.7 story transcends war. It speaks to a universal paradox that the pursuit of ultimate capability often undermines survival itself. Nations, corporations, even civilizations repeat that pattern. They build wonders that outstrip their capacity to sustain them. The German half-track is only one chapter in that longer human story, but perhaps its clearest one. The soldiers who drove it in 1945 understood none of this in theory, yet they understood everything in practice. They had filled its tank, watched the needle drop, and realized perhaps for the first time that history runs not on glory, but on fuel. By the 1960s, the Sd.Kfz.7 had passed fully into legend, its steel long melted down, but its lesson immortalized in manuals, doctrines, and boardrooms. What had begun as a technical curiosity became a moral parable about the limits of power and the price of waste. To the American mind, it represented a kind of victory more profound than any battle, the triumph of logistics over ideology, of endurance over brilliance. In newly declassified RAND archives from that decade, analysts revisited the data from captured German vehicles to refine a new discipline they called systems analysis, the science of balancing output cost and sustainability. In those documents, the Sd.Kfz.7's fuel consumption curves were redrawn alongside missile trajectory charts and bomber range tables. The principle was the same across all scales. Every act of movement consumes energy, and every empire collapses the moment it forgets that equation. Meanwhile, the cultural memory of the German half-track hardened into symbolism. Military historians like Basil Liddell-Hart and later Martin van Creveld would describe the Sd.Kfz.7 as a machine that revealed the Wehrmacht's soul, powerful, disciplined, and doomed by overconfidence. It joined the Tiger tank and the V-2 rocket in that pantheon of technological marvels that proved the limits of genius. The half-track was neither villain nor hero, merely the most honest mirror Germany ever built. For the United States, it had become an invisible teacher. When NASA engineers planned the Apollo lunar missions, they applied the same fuel-to-payload logic first derived from wartime vehicle studies. Every pound of weight and every drop of propellant had to serve a purpose. The principle that once governed the M3's gasoline range now governed the trajectories of spacecraft leaving Earth. Fuel is freedom, one engineer wrote in a 1964 internal memo, echoing without knowing it the field notes of a GI who had once cursed a thirsty German tractor outside Cologne. By then, the geopolitical landscape had shifted entirely. The Marshall Plan had rebuilt Europe into an industrial bloc powered by efficient production. The oil alliances forged in the late 1940s had matured into a global network that fed Western mobility. America had turned fuel efficiency into a form of soft power, from the pipelines of the Middle East to the assembly lines of Detroit. The quiet arithmetic that doomed the Sd.Kfz.7 now ruled the modern world, and yet the ghost of that vehicle still lingers. In museums from Koblenz to Fort Benning, its massive frame sits behind glass steel teeth of tracks frozen mid-bite, a relic of motion that could not last. Visitors marvel at its size, its precision, its presence. Few notice the small plaque at its base, range 155 miles road, 75 miles cross-country. That single statistic, buried among technical data, tells the entire story. Every nation since has tried to avoid the same trap. The Soviet Union built its tanks with crude efficiency. America developed its global logistics network into an art. When the Gulf War erupted in 1991, U.S. generals cited fuel planning as the foundation of their success. The chain that stretched from Saudi oil fields to the Kuwaiti desert was the descendant of the same supply web that once defeated Germany. Behind every Abrams tank and every Humvee lay the forgotten ghost of a Maybach engine that once ran dry outside the Rhine. Today, in an age of hybrid engines and digital warfare, the Sd.Kfz.7 remains unexpectedly relevant. Modern militaries still wrestle with the same paradox: how to balance capability with consumption. Drone fleets, aircraft carriers, and hypersonic weapons may seem distant from a 1940s half-track, but they share its fundamental constraint: the hunger for energy. The difference now is that the lesson has been learned, quantified, and enshrined in doctrine. Every new design is haunted by the question the GIs first asked in 1945. How far can it go before it runs out of fuel? When historians look back on the 20th century, they may see the Sd.Kfz.7 not merely as a German artifact, but as a turning point in human understanding. It marked the moment when armies and eventually civilizations began to realize that power without sustainability is self-defeating. The vehicle's hulking presence on the battlefield was impressive, but its empty tanks wrote the final chapter of the Third Reich. In the end, the Sd.Kfz.7 was more than a machine. It was a prophecy in steel, a warning that the future belongs not to the strongest, but to the most efficient. Its legacy outlived every general who commanded it, every factory that built it, and every ideology that praised it. Because beneath every engine, every convoy, and every empire, the same truth endures: victory belongs to those who can keep moving.